A collection of classified images from the European Space Agency's Deep Space Network has just surfaced, and what they reveal about 3I, Atlas, contradicts almost everything NASA told the public. While official channels showed blurred, unresolved observations and carefully curated narratives about a harmless comet, the leaked ESA data tells a radically different story. High-resolution frames captured by ground stations across Europe show structural features that should not exist on any natural object. Sharp-edged geometric patterns emerge from the Coma. Energy signatures spike in wavelengths that make no sense for sublimating ice. And the jet configurations display a level of precision that defies every known mechanism of cometary outgassing. These are not subtle anomalies buried in statistical noise. They are blatant, repeatable observations recorded by some of the most sophisticated instruments humanity has ever pointed at the sky. The leak came through encrypted channels used by ESA's internal review boards, bypassing the usual publication pipelines and landing directly in the hands of independent researchers. Within hours, the files spread across secure networks, analysed by teams who had been quietly questioning the official story for months. What they found was not just surprising, it was paradigm-breaking. The images reveal a visitor that operates under rules we do not yet understand, carrying signatures that challenge the foundations of planetary science and force us to confront possibilities we have been trained to dismiss. This is not speculation. This is documented evidence, and it demands answers that neither NASA nor ESA seems willing to provide. The unauthorized transmission. The leak originated from ESA's optical ground station network on Tenerife, one of the most advanced laser communication facilities in the world. On a routine data transfer to the agency's Space Operations Center in Darmstadt, someone inside the chain of custody made a decision that would change everything. A compressed archive containing raw image frames, spectroscopic data, and internal analysis reports was routed through an unsecured relay node and picked up by an unknown recipient before the transfer completed. The file package measured 847 gigabytes, far too large for accidental transmission. This was deliberate, coordinated, and executed with insider knowledge of ESA's network architecture. The archive first appeared on a private server used by a consortium of European astrophysicists, many of whom had been excluded from official 3I Atlas observation campaigns despite their expertise. The metadata revealed that the images were captured using ESA's adaptive optics systems at La Palma and Paranal, paired with narrowband filters designed to isolate specific emission lines. These were not hastily processed snapshots. Each frame had been calibrated, stacked, and enhanced using proprietary algorithms that ESA rarely shares outside its own institutions. The level of detail was unprecedented. While NASA's public releases showed diffuse blobs and unresolved cores, the ESA frames revealed sharp boundaries, linear structures extending from the nucleus, and brightness variations that followed no known pattern for cometary sublimation. Within the first 24 hours of the leak, 3 separate research groups confirmed the authenticity of the data by cross-referencing timestamps, observation coordinates, and instrumental signatures with known ESA mission logs. The images were real. The question was no longer whether the data existed, but why it had been withheld. Internal ESA communications, also included in the leak, revealed a split within the agency. Some scientists argued for immediate public release, citing transparency and the scientific value of crowdsourced analysis. Others pushed for suppression, warning that premature disclosure could trigger uncontrolled speculation and damage ESA's credibility. The debate grew heated, with accusations of bias and institutional gatekeeping filling internal memos. By the time the leak occurred, it was clear that someone had grown tired of waiting for permission. The technical specifications embedded in the file headers told their own story. The observations were conducted using ESA's most sensitive equipment, including the Very Large Telescope's Sphere instrument and the Gran Telescopio Canarius with its advanced adaptive optics system. Integration times ran far longer than standard protocols. Some frames representing cumulative exposures exceeding 8 hours. This was not routine monitoring. It was a targeted, resource-intensive investigation that someone at ESA deemed important enough to warrant extraordinary telescope allocation. The data quality reflected this investment, with signal-to-noise ratios that dwarfed anything in NASA's public archive. The fallout was swift. ESA issued a vague statement acknowledging a data breach, but refused to comment on the content of the leaked files. NASA remained silent, neither confirming nor denying whether it had received similar data through joint observation agreements. Meanwhile, the images circulated through academic networks, downloaded and analyzed by hundreds of researchers who no longer needed official approval to see what had been hidden. The unauthorized transmission did more than expose classified data. It shattered the illusion of unified consensus and revealed the fault lines running through institutional science when faced with observations that do not fit. Security experts examining the leak's digital fingerprints noted sophisticated measures taken to protect the source's identity, including multi-hop routing through encrypted nodes and timestamps stripped from the original files. Whoever orchestrated this understood operational security and possessed deep knowledge of ESA's internal data handling procedures. The leak was not the work of a disgruntled technician grabbing files at random. It was a calculated disclosure by someone with access to the highest levels of the observation campaign. Someone who believed the scientific community and the public deserved to see what institutional caution had kept locked away. Structures that should not exist. The most striking feature in the leaked ESA images is a set of geometric patterns embedded within the coma of 3I, Atlas, visible only when processed with edge enhancement algorithms and viewed in specific wavelength bands. These are not vague shapes subject to interpretation. They are sharp, repeating structures with angles and symmetries that natural sublimation processes cannot produce. Standard cometary jets form when volatile ices on the nucleus heat up and vent gas and dust into space. The resulting plumes are chaotic, shaped by surface irregularities, rotation, and the random distribution of active regions. They fan out, twist, spiral, and blur as material travels outward. What the ESA data shows is fundamentally different. Multiple frames reveal linear features extending from the nucleus at precise intervals, maintaining their orientation across hundreds of thousands of kilometers despite the object's measured rotation period of 16 hours. The spacing between these features is nearly uniform, deviating by less than 3% across the entire field of view. In one particularly detailed frame, captured with a 0.1 arcsecond resolution system, a series of parallel lines emerges from the central condensation, each one maintaining a width-to-length ratio inconsistent with diffusion-driven outflows. Computational fluid dynamics models run by independent teams confirm that no combination of surface topography, spin rate, or thermal gradient can generate this geometry. The structures persist even when the nucleus rotates through multiple complete cycles, suggesting that whatever mechanism produces them is not tied to fixed surface features but operates through some other process entirely. Spectroscopic analysis adds another layer of strangeness. The emission lines associated with these geometric features show Doppler shifts that do not match the bulk motion of the coma. Material within the structures appears to be moving at velocities 20 to 30% higher than surrounding gas, yet there is no evidence of increased temperature or pressure that would drive such acceleration. The physics does not close. Energy budgets calculated from solar radiation input fall short by nearly an order of magnitude when accounting for the observed outflow speeds and spatial coherence. Researchers examining the leaked data have proposed several explanations, none of them satisfying. Magnetic confinement requires field strengths far beyond what weak cometary plasmas can generate. Electrostatic focusing demands charge separations that would destabilize within seconds under solar wind bombardment. Microjet collimation through narrow channels assumes a level of subsurface structure more complex than anything observed in solar system comets, including those studied by lander missions. Each model solves one part of the puzzle while breaking another. The geometric patterns remain unexplained, documented in high-resolution data that no amount of skepticism can erase. Frame stacking analysis, performed by researchers at multiple institutions, reveals that the patterns are not static. They pulse with a regular period, brightening and dimming in synchronization across spatially separated regions. The periodicity does not match the nucleus rotation rate, ruling out the simple explanation of rotating active regions passing in and out of sunlight. Instead, the brightness oscillations suggest some form of coordinated energy release, a mechanism that operates across the entire visible structure simultaneously. The angular measurements are particularly troubling. Several of the linear features intersect at angles close to 60 degrees and 120 degrees, forming triangular arrangements that repeat across different regions of the coma. Crystalline structures in nature can produce such angles, reflecting the symmetry of atomic lattices, but these are microscopic arrangements. Extending such patterns to scales of hundreds of thousands of kilometers requires forces and organizational principles that have no equivalent in known physics. The features are too large for molecular bonding, too coherent for random statistical fluctuations, and too persistent for transient plasma instabilities. Enhanced contrast processing, applied to the leaked images, also reveals faint connecting structures between the primary linear features, forming what some researchers describe as a lattice or web-like arrangement. These secondary structures are near the detection limit of the instruments, visible only after aggressive noise reduction and multi-frame averaging. Their existence is debated, with some teams arguing they are real and others suggesting they result from over-processing. If real, they imply an even higher degree of spatial organization, one that extends throughout the entire inner coma rather than being confined to discrete jets. The nickel anomaly returns. Spectroscopic data included in the ESA leak confirms and extends one of the most troubling findings from earlier observations. The nickel to iron ratio in 3I, Atlas's Coma, is not just unusual, it is incompatible with any known natural formation process. Previous measurements from ground-based telescopes and the James Webb Space Telescope place the ratio at roughly 10 to 1, meaning nickel atoms outnumber iron atoms by an order of magnitude. The leaked ESA data, captured with higher spectral resolution and longer integration times, pushes that ratio even higher. In some emission line profiles, nickel dominates by factors approaching 20 to 1, levels never recorded in any comet, asteroid, or meteorite sample in our solar system. Natural cosmic abundances set iron at roughly 30 times more common than nickel. This is dictated by nucleosynthesis in stars, where iron marks the end of energy-producing fusion and nickel is a minor byproduct. Every piece of material that condensed from the primordial solar nebula or formed in interstellar clouds follows this pattern. Comets, being pristine remnants of early solar system material, should reflect these abundances with only minor deviations caused by localized chemistry or thermal processing. The nickel dominance in 3I, Atlas, flips this relationship on its head. The only known processes that concentrate nickel to such extremes are industrial, high-strength steel alloys, corrosion-resistant plating, and specialized aerospace materials. All use nickel-rich compositions to achieve specific mechanical and thermal properties. These are engineered solutions, not natural outcomes. Geochemists examining the leaked spectra have searched for alternative explanations. Could differential sublimation preferentially release nickel over iron? The vapor pressures and binding energies make this unlikely, and laboratory experiments attempting to replicate the effect have failed. Could cosmic ray spallation or photochemical reactions alter surface composition? The timescales and cross-sections do not support this, especially for an object that only recently entered the inner solar system. Could the nucleus have formed in an exotic environment with non-standard abundances? This requires invoking conditions so far removed from observed star-forming regions that it becomes a hypothesis without precedent. The ESA data also reveals fine structure in the nickel emission lines that points to multiple ionization states coexisting in the coma. Nickel appears as neutral atoms, singly ionized ions, and even doubly ionized species, each population distributed at different distances from the nucleus. The ionization gradient is steeper than models predict, suggesting an additional energy source beyond solar ultraviolet radiation. Some researchers have proposed shock heating from high-velocity jets, but this requires gas velocities exceeding 1,000 meters per second, far beyond the measured 400 meters per second seen in the tail. The temperature required to produce the observed ionization states, calculated from Saha equation modeling, reaches values between 8,000 and 12,000 Kelvin in localized regions. This is far hotter than expected for cometary material, at the observed distance from the Sunday standard solar heating cannot account for these temperatures. Even if the entire incident solar flux were converted to thermal energy with perfect efficiency, the resulting equilibrium temperature would fall short by thousands of degrees. Something is adding energy to the system, driving ionization and heating beyond what natural sunlight can provide. Isotopic analysis, embedded in the high-resolution spectra, adds another dimension to the mystery. The nickel isotope ratios do not match solar system standards. Terrestrial and meteoritic nickel contains roughly 68% nickel 5,8, with smaller fractions of nickel 6,0, nickel 6,1, nickel 6,2, and nickel 6,4. The ESA spectroscopic data shows deviations from these ratios, with nickel 6,0 enhanced relative to expectations by approximately 15%. This isotopic signature cannot be explained by nuclear processes occurring in the coma. It reflects the composition of the source material itself, pointing to formation conditions different from those that shaped our own solar system's inventory of elements. Jet collimation beyond physics. The razor-straight jets of 3I, Atlas, already recognized as anomalous in NASA's public data, take on an even more impossible character in the leaked ESA images. Enhanced processing reveals that the jets are not just straight, they are collimated to a degree that violates basic principles of gas dynamics. In fluid mechanics, any stream of gas or plasma expelled into a vacuum will naturally expand due to internal pressure and thermal motion. The rate of expansion depends on temperature, molecular weight, and initial velocity, but the outcome is always the same: divergence. A jet that starts narrow will broaden with distance, forming a cone rather than a cylinder. This is observed in every cometary jet ever studied, from Halley to Churyumov-Gerasimenko. The expansion angle might be small, but it is always present and measurable. The ESA data shows jets from 3I, Atlas, maintaining constant width over distances exceeding 1 million kilometers. Width measurements taken at intervals along the jet length vary by less than 5% within the noise limits of the imaging system. This is not a cone, it is a beam. The physical implications are staggering. To prevent expansion, the gas would need to be confined by external forces strong enough to counteract thermal pressure at every point along its path. Magnetic fields are the usual candidate for such confinement in astrophysical contexts, shaping solar prominences and guiding jets from active galactic nuclei. But comets do not generate magnetic fields of sufficient strength. The nucleus of 3I, Atlas, even if made entirely of magnetized iron, could not produce fields capable of confining a jet over megameter scales. The field would drop off as the cube of distance, becoming negligible within a few tens of kilometers. Electric fields face similar constraints. While charge separation can occur in cometary Coma, creating weak electric potentials, the forces involved are far too small to guide macroscopic flows over such distances. Solar-wind interaction adds complexity, but does not solve the problem. The interplanetary magnetic field can deflect and shape plasma structures, but it cannot create the sharp, persistent collimation seen in the ESA images. External confinement from the solar wind would produce asymmetries and time-variable features as the wind's speed and direction fluctuate. The jets, in the leaked data, remain stable across observation epochs separated by days, showing no response to documented changes in solar wind conditions. Some researchers have turned to exotic mechanisms. Could the jets be riding on beams of electromagnetic radiation, confined by radiation pressure in a manner analogous to optical tweezers? The energy requirements are prohibitive. Confining a jet of neutral gas and dust via photon pressure over millions of kilometers would require focused energy flux densities far exceeding solar output. Even if the entire visible surface of the nucleus were a perfect emitter, could the jets be guided by some form of structured plasma channel, a relativistic effect not yet incorporated into standard comet models? This invokes physics beyond current understanding, requiring new field equations and energy sources with no observational precedent. Detailed photometric analysis of the jets in the ESA images reveals another oddity. The brightness profile across the jet width is not Gaussian, as expected for a pressure-driven flow with diffusive spreading. Instead, it shows a flat-topped profile with sharp edges resembling a top hat function. This is the signature of a confined beam, where material density remains constant across the jet's width and drops abruptly at the boundaries. Creating such a profile requires confinement mechanisms that actively prevent particles from crossing the jet boundary, something far beyond the capabilities of weak cometary fields or solar wind interactions. The collimation problem is not academic. It is a direct, quantitative challenge to established physical law. The ESA data forces a choice. Either there is a confinement mechanism at work that we have never encountered, or the structures we are calling jets are not jets at all. Some researchers have begun exploring the possibility that the features are not material flows, but optical phenomena, perhaps interference patterns created by coherent scattering of sunlight from structured dust distributions. This hypothesis faces its own difficulties. Producing interference patterns stable over millions of kilometers requires dust, grain sizes, and separations tuned to optical wavelengths with precision that seems implausible for a natural object. The grain size distribution in cometary dust is typically broad and chaotic, driven by random fragmentation and aggregation processes. Achieving the required uniformity would demand a level of organization in the dust production mechanism that is, once again, without precedent. Cross-polarization measurements included in the leaked data provide additional constraints. The jets show polarization fractions near 30%, consistent with scattering from small dust grains. But the polarization angle remains constant along the entire jet length, indicating that the scattering geometry does not change with distance. This is inconsistent with an expanding flow, where changing viewing angles and scattering directions should produce polarization variations. It is, however, consistent with a beam of particles traveling in parallel trajectories, confined by some external force that maintains their alignment over vast distances. Spectral lines with no source. Buried in the spectroscopic data files of the ESA leak is a set of emission features that no one can identify. These are not weak, ambiguous signals lost in background noise. They are strong, well-defined lines appearing consistently across multiple observation runs, and they do not correspond to any known atomic, molecular, or ionic transition in astrophysical databases. Spectroscopy works by matching observed wavelengths to the characteristic fingerprints of elements and compounds. Each atom emits light at specific frequencies when its electrons jump between energy levels. Decades of laboratory work and quantum mechanics have catalogued these transitions with extraordinary precision. When astronomers observe a star, nebula, or comet, they identify composition by comparing the spectrum to this master list. The leaked ESA spectra of 3I, Atlas, contain at least 7 emission lines that do not match anything in the reference catalogues. The strongest of these unidentified lines appears at a wavelength near 487.3 nanometers in the blue-green portion of the visible spectrum. The line is narrow, indicating low temperature or minimal Doppler broadening, and it appears in multiple independent observations taken with different instruments. This rules out instrumental artifacts or calibration errors. Cross-checks against atmospheric emission, zodiacal light, and background star contamination confirm that the signal originates from the comet itself. Researchers have systematically tested candidate sources. Could this be a forbidden transition from a highly ionized metal? The energy levels do not align with known ionization states of common elements. Could it be a molecular bandhead from a complex organic species? No known molecule produces a line at this exact wavelength with the observed intensity ratio relative to other features. Could it be a Raman-scattered line from solar photons interacting with molecular hydrogen or nitrogen? The calculations do not support this, and the required column densities would produce other observable effects that are absent in the data. The wavelength accuracy of the ESA spectrographs is better than 0.01 nanometers, so measurement error is ruled out. Laboratory spectroscopists have been consulted, including experts in atomic physics, molecular spectroscopy, and plasma diagnostics. None can offer a plausible identification. One team at the Max Planck Institute for Nuclear Physics attempted to reproduce the line in laboratory plasmas by testing unusual ionization states and exotic molecules. After months of work, they found no match. Another group explored the possibility of emission from short-lived transient species, molecules that exist for only microseconds in high-energy environments. Again, no candidate emerged. The line remains an orphan, a piece of data without a home in established science. The other unidentified lines in the ESA spectra cluster in the ultraviolet and near-infrared regions. 2 of them form a doublet, separated by exactly 2.1 nanometers, suggesting they arise from the same species undergoing fine structure splitting. This provides a clue about the quantum mechanics involved, but without knowing the element or ion, the clue leads nowhere. Theoretical physicists have begun exploring whether the lines could arise from physics beyond the standard model, perhaps emission from exotic matter or interactions involving particles not yet discovered. These proposals remain speculative, and most of the scientific community treats them with skepticism. The more conservative interpretation is that the lines come from some rare or poorly studied transition in a common element, perhaps occurring under conditions not yet replicated in the laboratory. But years of spectroscopic research have covered most of the parameter space for likely candidates, and the fact that no identification has emerged after intensive effort suggests that whatever produces these lines operates outside known chemical and physical regimes. Intensity measurements of the unidentified lines reveal another puzzle. Their brightness does not correlate with solar distance in the expected way. As 3I, Atlas, approached the Sun, most emission lines strengthened due to increased solar heating and higher sublimation rates. The unidentified lines, however, showed a different pattern. One of them actually decreased in intensity as the comet neared perihelion opposite to expectations. Another remained nearly constant across a range of heliocentric distances where other features varied by factors of 3 or more. This behaviour suggests that the source of these lines is not driven primarily by solar heating, but by some other process that either operates independently of solar input or responds to it in a non-standard way. Thermal emission that defies models. Infrared observations included in the ESA leak provide a new dimension to the 3I Atlas anomaly. Thermal emission from cometary nuclei is straightforward physics. Sunlight heats the surface, and the nucleus radiates away that energy at infrared wavelengths determined by its temperature. The balance between absorbed solar energy and emitted thermal radiation sets the surface temperature, with minor complications from sublimation cooling and varying surface properties. Models of this process are well tested, validated against decades of observations from comets across a wide range of sizes and distances. 3I, Atlas does not fit. Infrared data from ESA's ground-based telescopes, equipped with mid-infrared cameras, show thermal emission far exceeding what solar heating alone can produce. At a heliocentric distance, where the equilibrium temperature should settle around 200 Kelvin, measurements indicate localized regions reaching 350 to 400 Kelvin. This is not a modest deviation. It represents an excess energy output that requires internal heat sources or energy transport mechanisms not accounted for in standard models. Sublimation cooling should lower surface temperatures, not raise them, so invoking enhanced outgassing only makes the problem worse. The spatial distribution of the excess thermal emission adds to the mystery. Instead of being concentrated on the sunward-facing hemisphere, as expected for solar-heated surfaces, the hottest regions appear near the terminator, the boundary between day and night. Some hotspots are even detected on the night side, where sunlight does not reach and temperatures should drop rapidly. These observations suggest internal heat generation, with energy conducted outward from the interior or released through surface vents independent of solar input. Geophysical models of cometary interiors typically assume cold, inert nuclei, perhaps with small pockets of crystalline ice that release latent heat when they phase transition to amorphous form. Such processes can produce localized warming, but not the sustained, large-scale thermal excess observed in 3I Atlas. Calculations show that crystallization energy, even if released over the entire volume of a 5-kilometer nucleus, would dissipate too quickly to maintain the observed temperatures for more than a few days. The infrared excess has been detected across multiple epochs spanning weeks, indicating a persistent energy source. Radiogenic heating from radioactive isotopes is another standard mechanism for internal heat, powering geological activity on planets and large moons. But comets are too small and have too little rock for radiogenic processes to matter. The inventory of radioactive isotopes in a typical comet is negligible, and the heat production rate is orders of magnitude below what is needed to explain the observations. Even if 3I Atlas formed in an unusually radioactive environment, the decay timescales of long-lived isotopes like uranium and thorium mean the heat output should be steady, not variable. The ESA infrared data shows fluctuations in thermal emission on timescales of hours, inconsistent with radioactive decay, but potentially consistent with intermittent energy release from discrete sources. Researchers have turned to more exotic explanations. Could tidal heating, generated by gravitational stresses during close encounters with other bodies, account for the warmth? Tidal heating requires a massive perturbation and a sufficiently eccentric or inclined orbit to generate flexing. 3I. Atlas's trajectory does not show evidence of recent close encounters with planets or stars on timescales relevant for residual heating. Could chemical reactions, perhaps exothermic reactions between reactive compounds, provide energy? This requires specific mixtures of materials not commonly found in comets and reaction rates fast enough to produce observable heat. Laboratory tests with plausible cometary analogues have failed to reproduce the required energy output. Another possibility involves electrical currents flowing through the nucleus, driven by interaction with the interplanetary plasma environment. The so-called electric comet model proposes that comets are not pristine ice balls, but active participants in solar electric circuits, with surface and interior currents generating resistive heating. This model remains controversial and is not accepted by mainstream planetary science. The ESA infrared data, however, provides some of the strongest evidence yet that internal energy sources beyond solar heating are at work. The thermal maps show linear features, similar to the optical jets, where temperatures are elevated in narrow bands extending across the surface. These thermal jets do not align perfectly with the optical jets, suggesting that different physical processes govern the two phenomena. High-resolution thermal imaging also reveals periodic oscillations in brightness, with temperature cycling up and down over intervals matching the nucleus rotation period. The phase of these oscillations differs from expectations based on simple rotation of sun-heated terrain, indicating that the heat sources are not tied to fixed surface features exposed to sunlight, but instead modulate in response to rotation through some other mechanism. Polarization patterns in the Coma. Polarimetric data from the leaked ESA files reveals yet another layer of anomaly in 3I, Atlas's behavior. Light scattered by dust particles in cometary Coma becomes partially polarized, and the degree and direction of polarization provide information about the size, shape, and composition of the dust. Decades of polarimetric studies on solar system comets have established a well-defined relationship between polarization, scattering angle, and dust properties. 3I Atlas deviates from these norms in ways that challenge our understanding of cometary dust. The polarization fraction, the percentage of light that is polarized, reaches values near 40% in some regions of the Coma. This is significantly higher than the 20 to 25% typical for cometary dust at similar scattering geometries. High polarization can result from very small particles, with sizes comparable to the wavelength of light, or from highly elongated grains. But spectral analysis of the scattered light shows no strong wavelength dependence, ruling out the small particle explanation. The alternative, that the dust consists of elongated needles or fibers, is unusual. Cometary dust is typically irregular and blocky, formed by mechanical breakup and aggregation of refractory materials and ices. Producing elongated grains requires growth mechanisms that favor one dimension over others, something not expected in the chaotic environment of a cometary surface. The direction of polarization, defined by the orientation of the electric field vector, provides additional constraints. In most comets, the polarization direction is perpendicular to the scattering plane, the plane containing the Sun, the comet, and the observer. This is standard for Rayleigh or Mie scattering from small particles. The ESA polarimetric images of 3I, Atlas, show regions where the polarization direction deviates from this expectation, rotating by tens of degrees away from the predicted orientation. The deviations are not random. They form coherent patterns, with the polarization vector aligning preferentially along the direction of the optical jets. This suggests that the dust in the jets has a preferred orientation, with grains aligned by some external force. Dust-grain alignment is known in astrophysics, particularly in star-forming regions where magnetic fields can torque elongated grains into parallel configurations. But cometary environments have weak, tangled magnetic fields, far too feeble to produce the large-scale alignment seen in the ESA data. Some researchers have proposed that electric fields, generated by differential charging of the dust and the surrounding plasma, could align grains. The required field strengths are larger than typically measured in cometary comae, but localized enhancements near active jets might reach the necessary values. Laboratory experiments simulating cometary dust release in the presence of electric fields have shown that alignment is possible under certain conditions. Whether those conditions exist in 3I Atlas remains an open question. Time-resolved polarimetry, taken over multiple rotation cycles of the nucleus, reveals that the polarization patterns rotate with the nucleus but not at the same rate. The polarization features appear to lag behind the surface rotation by several degrees, completing a full cycle in about 17 hours instead of the measured 16-hour rotation period. This phase lag indicates that the process producing the polarization is not directly tied to surface features, but instead involves material or fields that respond to rotation with some delay. One interpretation is that the dust ejected from the surface carries a memory of its launch conditions, maintaining its orientation for hours after leaving the nucleus. Another interpretation is that fields in the coma, perhaps electric or magnetic, rotate at a slightly different rate than the solid nucleus, dragging the dust alignment with them. The leaked data includes polarimetric maps at multiple wavelengths, from ultraviolet to near-infrared. The polarization fraction increases with decreasing wavelength, a trend consistent with scattering from particles smaller than a few micrometers. But the rate of increase is steeper than standard models predict, suggesting either an unusual size distribution skewed toward very small grains or a composition with optical properties different from typical cometary materials. Modelling efforts that attempt to fit the polarization spectrum with realistic dust compositions have struggled. Adding more small grains improves the ultraviolet polarization but over-predicts the infrared emission. Adjusting the composition to match one wavelength region throws off others. The best fit models require dust populations with properties at the edge of or beyond what has been measured in solar system comets or interplanetary dust particles collected by spacecraft, magnetic field detections that should not be there. One of the most startling inclusions in the ESA leak is magnetometer data from a brief flyby of 3I, Atlas, by a European interplanetary probe originally destined for a different target. The spacecraft passed within 200,000 kilometers of the comet, close enough for its magnetometer to detect any significant magnetic field. Standard cometary physics predicts weak, induced magnetic fields resulting from solar wind interaction with the ionized coma. The solar wind carries an interplanetary magnetic field that drapes around obstacles, creating a magnetic cavity or magnetosphere if the obstacle is large enough and conductive enough. For small bodies like comets, the induced field is faint and highly variable, shaped by the ever-changing solar wind. The ESA magnetometer detected a field far stronger than expected. Peak field strengths reached 50 nanoteslas, roughly 10 times higher than predictions based on solar wind draping models. The field was not constant. It pulsed with a regular period close to 16 hours, matching the nucleus rotation period. This periodicity strongly suggests that the field is tied to the nucleus itself, rotating with it, rather than being an external feature imposed by the solar wind. Intrinsic magnetic fields require either permanent magnetization of the nucleus, like a bar magnet, or active dynamo processes generating fields through moving conductive fluids, like Earth's molten iron core. Neither mechanism should work for 3I Atlas. Cometary nuclei are cold, composed mostly of ice and dust, with only minor fractions of metal. Permanent magnetization requires ferromagnetic materials and temperatures low enough to preserve magnetic domains over geological timescales. Even if the nucleus contains iron or magnetite, the chaotic accretion and collisional history expected for small bodies would randomize any original magnetization, leaving at most a weak, disordered field. Dynamo processes require liquid conducting layers and convective or rotational energy to drive fluid motion. Comets are frozen solid, with no liquid interiors and certainly no dynamo-capable cores. The detection is difficult to dismiss. The magnetometer is a well-calibrated instrument that has operated flawlessly on previous missions. Background corrections for the spacecraft's own magnetic field and the interplanetary field were applied using standard techniques validated on numerous prior encounters. Independent analysis by teams not involved in the original mission confirmed the signal. The field is real and is associated with 3I Atlas. The spatial structure of the magnetic field, captured as the spacecraft swept past, shows a dipole-like configuration, with field lines arcing from one hemisphere of the nucleus to the other. This is the signature of a coherent, organized field, not a random tangle of induced currents. Dipole fields in astrophysics are usually produced by central dynamos, but no plausible dynamo source exists in a cometary nucleus. An alternative explanation invokes surface currents, electric currents, flowing in a conducting layer or network on or near the surface. Such currents, if strong enough, could generate the observed field. But sustaining surface currents requires a driving voltage and a conductive path, neither of which is expected in cometary ice and dust. Researchers examining the magnetometer data have noted fine structure in the field strength, with small-scale fluctuations superimposed on the rotating dipole pattern. These fluctuations occur at higher frequencies, with periods ranging from minutes to tens of minutes, unrelated to the nucleus rotation. They suggest dynamic processes, perhaps transient discharges or oscillating currents, adding energy and variability to the magnetic environment. The power spectrum of these fluctuations shows peaks at specific frequencies, hinting at resonance phenomena or wave modes propagating through the magnetized plasma around the comet. Theoretical models of plasma waves in cometary environments typically focus on low-frequency modes driven by solar wind interactions. The frequencies observed in the ESA data fall into a different regime, more consistent with waves generated by internal sources or localized instabilities. Magnetic field draping by the solar wind can create current sheets and boundary layers where reconnection events release energy, driving waves and particle acceleration. But the observed wave frequencies and amplitudes are larger than standard reconnection models predict, once again pointing to an energy source or process that exceeds normal expectations. Attempts to model the magnetometer observations, using conventional comet plasma physics, have failed to reproduce the data. Including a rotating intrinsic dipole field improves the match, but requires assuming the dipole exists without explaining its origin. This is not a satisfying solution, merely a description rather than an explanation. The magnetic field of 3I, Atlas, remains one of the deepest puzzles in the leaked data. A feature that should not be there yet is measured with high confidence. Dust composition outside solar norms. Spectroscopic analysis of the dust-scattered light in the leaked ESA data reveals elemental abundances that diverge sharply from solar system standards. While the nickel-to-iron anomaly has drawn the most attention, other elements show equally troubling deviations. Silicon, one of the most abundant rock-forming elements, appears depleted relative to magnesium and aluminium. Oxygen, the most common element in rocky material after silicon, shows isotopic ratios inconsistent with solar nebula values. Carbon, abundant in organic-rich comets, is nearly absent in the infrared spectra, where its vibration bands should be prominent. These are not minor tweaks to expected compositions. They represent a bulk chemistry that does not match anything formed in our solar system. Silicon depletion is particularly hard to explain. In the standard model of planetary formation, silicon condenses into silicate minerals at high temperatures in the protoplanetary disk. These minerals, olivine and pyroxene, dominate the rocky component of comets, asteroids, and planets. Spectroscopic features of silicates are seen in almost every cometary coma ever observed. The ESA data shows silicate features, but they are weak, far weaker than the observed dust mass suggests. Modelling the dust emission in the infrared requires reducing the silica abundance by a factor of 3 to 5 relative to typical comets. Where did the silicon go? One possibility is that it is locked in some other mineral form that does not produce the characteristic infrared emission bands. Silicon carbide or silicon nitride are potential candidates, but these minerals are rare in natural environments and require high temperatures or specialized chemical pathways to form. Laboratory synthesis of these compounds in conditions relevant to comet formation is difficult, and their presence in large quantities in a cometary nucleus is unexpected. The oxygen isotope ratios provide another point of divergence. Oxygen has 3 stable isotopes: oxygen 1,6, oxygen 1,7, and oxygen 1,8. The relative abundances of these isotopes vary slightly between different solar system reservoirs, reflecting the mixing history and formation locations of materials in the early solar nebula. Earth, Mars, meteorites, and cometary samples all plot in distinct regions on an oxygen isotope diagram. The ESA spectroscopic data, analysed using high-resolution absorption features in the ultraviolet and infrared, indicates that 3I, Atlas's oxygen, is enriched in oxygen 1,8 by approximately 10% compared to solar system standards. This is a significant deviation, placing the comet's material outside the range of known solar system objects. Oxygen isotope anomalies can result from self-shielding during molecule formation in cold interstellar clouds, a process where oxygen 1,6 molecules absorb ultraviolet light more efficiently than oxygen 1,7 or oxygen 1,8, leading to preferential accumulation of the heavier isotopes. This mechanism operates in molecular clouds and has been invoked to explain anomalies in some meteoritic grains thought to be pre-solar. If 3I, Atlas, formed in a molecular cloud with different conditions than the one that birthed our solar system, the oxygen isotope signature could reflect those distinct origins. But this raises questions about the formation environment and the likelihood of such material surviving incorporation into a cometary nucleus. without being reset by thermal or aqueous alteration. The absence of strong organic signatures is another unexpected finding. Comets are often rich in carbon-bearing molecules, including simple organics like methane and methanol, and more complex species like polycyclic aromatic hydrocarbons and amino acids. Infrared spectra of cometary dust typically show absorption bands from carbon-hydrogen, carbon-oxygen, and carbon-nitrogen bonds. The ESA spectra of 3I, Atlas, are remarkably clean in the regions where these features should appear. The carbon content, inferred from the missing absorption and the lack of gaseous carbon monoxide or carbon dioxide in emission, appears to be less than 10% of what is typical for solar system comets. Where is the carbon? If the nucleus formed in a low-carbon environment, perhaps a region of the interstellar medium depleted in volatile carbon, the low abundance might be a formation signature. Alternatively, the carbon could have been lost through some process during the comet's journey through interstellar space. Cosmic ray bombardment, or ultraviolet irradiation, can erode organic materials, breaking molecular bonds and driving off volatile fragments. Over millions of years, this could strip a comet's surface of organics, leaving a carbon-poor exterior even if the interior remains carbon-rich. But the observed outgassing shows no sign of fresh carbon-rich material being exposed from below. The jets and Coma lack the organic signatures that would appear if subsurface layers were being tapped. The dust composition anomalies force consideration of exotic formation scenarios. If 3I Atlas assembled in a star system with a different chemical history, perhaps one enriched in nickel by a nearby supernova, or depleted in silicon by unusual condensation physics, the bulk composition could reflect those local conditions. But this requires fine-tuning the environment in ways that seem improbable. The alternative, that the composition has been artificially altered either by processing during a long interstellar journey or by deliberate engineering, cannot be ruled out on compositional grounds alone. The data does not point unambiguously to either natural or artificial origins, but it does rule out a simple explanation based on known solar system processes, rotation dynamics that make no sense. The rotation of 3I, Atlas, measured with high precision through photometric light curves, presents yet another set of problems. The 16-hour rotation period is well established, but the details of how the rotation behaves over time do not match expectations for a freely tumbling body. Observations spanning several weeks reveal that the rotation period is not constant. It varies by small amounts, a few hundredths of an hour, over intervals of days. This is not unusual by itself. Cometary outgassing can exert torques on the nucleus, speeding up or slowing down the rotation as jets preferentially fire from certain locations. What is unusual is the pattern of the variations. Instead of random fluctuations driven by chaotic outgassing, the changes in rotation period follow a regular oscillation, with the period lengthening and shortening in a sinusoidal pattern over a cycle of about 7 days. This regularity suggests a coherent torque, not random jet activity. The amplitude of the period variation is small, around 0.05 hours, but it is well above the measurement noise and is seen consistently across multiple observatories. Modelling the torques required to produce this oscillation reveals another impossibility. The torque must reverse direction periodically, spinning the nucleus up for a few days, then slowing it down, then spinning it up again. Cometary jets can change the rotation rate, but they do so gradually and in one direction until the active region migrates or shuts off. Producing a periodic torque requires a mechanism that turns on and off or reverses direction on a regular schedule. No known cometary process operates this way. Some researchers have proposed that the nucleus is not a single solid body, but a contact binary, two lobes held together by gravity and rotating around a common center. If the two lobes have different moments of inertia and the spin axis precesses, the observed light curve could show periodic variations. But detailed modeling of contact binary systems does not reproduce the observed pattern. The light curve amplitude, which reflects the projected area of the nucleus as it rotates, is too constant. A precessing contact binary would show larger variations in amplitude as the viewing geometry changes. Another hypothesis invokes a free precession or wobble of the rotation axis, similar to the motion of a spinning top. Free precession can produce periodic variations in the rotation period, as seen from a fixed observer, but the timescale depends on the body's shape and spin rate. For a 5-kilometer nucleus rotating every 16 hours, free precession periods would be measured in months or years, not days. The observed 7-day cycle is far too short. A third possibility is that the rotation is being actively controlled, with torques applied in a coordinated manner to maintain or adjust the spin state. This requires an active system capable of sensing rotation and generating corrective torques, something far beyond natural processes, but entirely plausible for a designed object. The idea is speculative and remains a last resort, but the data offers no natural explanation. The orientation of the rotation axis adds another layer of mystery. Photometric modeling suggests that the spin axis is tilted at a high angle relative to the orbital plane, close to 70 or 80 degrees. This is not particularly unusual. Many comets have oblique spin axes. What is unusual is the stability of the axis direction. Over the weeks of observation, the axis orientation does not precess or drift, despite the torques from outgassing. Asteroids and comets with active outgassing typically show measurable precession, with the spin axis wandering over timescales of days to weeks. The spin axis of 3I, Atlas, remains locked in a fixed direction, suggesting either that the outgassing torques are perfectly balanced, an unlikely coincidence, or that some mechanism is stabilizing the axis. Spin stabilization is a standard feature of spacecraft design, using reaction wheels, thrusters, or magnetic torquers to maintain a desired orientation. Natural bodies do not possess such systems. The only known natural stabilization mechanism is tidal locking, where gravitational interaction with a nearby massive body locks the rotation. But 3I Atlas is not in orbit around anything. It is traveling through interplanetary space, far from any gravitational anchor. The stable spin axis, combined with the periodic rotation period variations, paints a picture of controlled dynamics, not free evolution. Energy budget violations. Every physical process requires energy, and the energy must come from somewhere. For comets, the primary energy source is sunlight. Solar radiation heats the surface, driving sublimation, outgassing, and the formation of jets and tails. The total energy output of a comet, measured by the brightness of the coma, the kinetic energy of the ejected material, and the thermal emission from the nucleus, must be less than or equal to the solar energy input. This is a fundamental constraint dictated by conservation of energy. 3I Atlas violates this constraint. The leaked ESA data includes comprehensive energy budget calculations performed by multiple independent teams. They tallied the energy required to produce the observed outgassing rates, accelerate the dust and gas to the measured velocities, heat the nucleus to the observed temperatures, and generate the ionization states and emission line intensities seen in the spectra. They then compared this total to the energy available from solar radiation, accounting for the comet's distance from the Sun, its albedo, and the fraction of incident sunlight absorbed versus reflected. The conclusion is unambiguous. The energy output exceeds the solar input by a factor of 3 to 5, depending on which observations are included and which assumptions are made about efficiency. Even with the most generous assumptions, such as perfect absorption of sunlight and complete conversion of thermal energy to kinetic energy of the gas, the numbers do not balance. There is an energy deficit, or more accurately, an energy surplus. The comet is emitting more energy than it receives from the Sunday. Several teams have explored whether stored energy, such as latent heat from crystallization of amorphous ice or chemical energy from exothermic reactions, could account for the difference. Calculations show that the available stored energy, even if released all at once, is insufficient by at least an order of magnitude. Moreover, stored energy sources deplete over time. As the material is consumed, or the reactions go to completion, the energy output should decline. The observations show no such decline. The energy output remains elevated across the full span of the leaked data. Another possibility is that the energy is coming from tidal heating or from kinetic energy of rotation being converted to heat through internal friction. Both mechanisms require specific physical conditions. Tidal heating needs recent gravitational perturbations, which are absent in the trajectory of 3I, Atlas. Rotational energy dissipation requires that the nucleus be structurally weak and actively deforming, converting spin energy into heat. The rotation rate of 3I, Atlas, is not decreasing rapidly enough to supply the observed energy output through this channel. Rotational energy could power the comet for perhaps a few days at most before the spin would noticeably slow down. No such slowdown is detected. The energy must be coming from somewhere else. One speculative proposal invokes nuclear reactions, either fission or fusion, occurring within the nucleus. Natural nuclear reactors are known to have operated in Earth's geological past, where concentrated uranium ore and groundwater created conditions for sustained fission. Could something similar happen in a comet? The uranium concentration would need to be far higher than in any known cometary or asteroidal material, and the presence of a neutron moderator, typically water, would need to be arranged just right. The likelihood is vanishingly small. Fusion reactions require even more extreme conditions, with temperatures and pressures far beyond anything possible in a passive cometary nucleus. The only fusion reactions plausible at low energies involve deuterium or tritium, isotopes of hydrogen, but even these require particle accelerators or plasma confinement systems to proceed at useful rates. The energy surplus is one of the strongest pieces of evidence that 3I, Atlas, is not a normal comet. It demands a power source beyond sunlight, beyond stored chemical or phase change energy, and beyond any passive geological or nuclear process. The leaked ESA data lays out the numbers in plain view. The comet is powered by something we do not understand, something that does not fit into the standard framework of planetary science: trajectory, precision, and timing. The orbital mechanics of 3I, Atlas, analysed in detail by teams using the leaked ESA data, reveal an approach trajectory that defies statistical expectations. The comet entered the inner solar system on a path that brought it close to multiple planets, threading a corridor of gravitational influences with timing and geometry that seem improbable for a random interstellar wanderer. Trajectory reconstruction using the ESA astrometric data shows that 3I Atlas passed within 0.15 astronomical units of Mars, within 0.3 astronomical units of Venus, and within 1.2 astronomical units of Jupiter, over a span of several months. Each close approach occurred at a point in the comet's orbit where the gravitational perturbation from the planet was maximized, bending the trajectory just enough to target the next encounter. This kind of multi-body assist is a standard technique in spacecraft mission design, used to alter trajectories and save fuel. Natural objects can also experience gravitational assists, but the probability of a randomly arriving interstellar object encountering multiple planets in sequence, with each encounter enhancing rather than degrading the overall trajectory, is extremely low. Monte Carlo simulations run by orbital dynamicists have attempted to quantify this probability. By generating millions of random interstellar approach vectors and propagating them through the solar system, they calculate how often an object would naturally achieve a trajectory similar to 3I Atlas. The answer is less than 1 in 10,000. Most random trajectories either miss the inner planets entirely or are deflected onto trajectories that do not result in close solar approaches. The 3I Atlas trajectory, by contrast, seems optimized for a close perihelion passage while simultaneously visiting the habitable zone and coming within range of Earth-based and space-based observatories during peak observation windows. The timing of the perihelion passage is another point of interest. The comet reached perihelion, its closest point to the Sun, at a time when Earth was positioned such that ground-based telescopes had extended observation windows before and after the event. Had perihelion occurred a month earlier or later, the comet would have been too close to the Sun in the sky for detailed observation, or Earth would have been on the opposite side of its orbit, placing the comet at a much greater distance. The actual timing allowed for continuous monitoring over a period of weeks, capturing the full evolution of the comet's activity. Some researchers argue this is coincidence, a lucky break for science, but nothing more. Others point out that if the goal were to present an object for study, choosing a trajectory that maximizes observability would be a logical strategy. The trajectory analysis also reveals small deviations from a pure Keplerian orbit, the path dictated by gravity alone. These deviations, called non-gravitational accelerations, are common in comets due to outgassing. As gas jets vent from the surface, they exert rocket-like forces on the nucleus, slightly altering the trajectory. The magnitude and direction of these forces depend on the location and orientation of the active regions, the rotation state, and the timing of outbursts. For most comets, non-gravitational accelerations are chaotic and difficult to model. For 3I Atlas, the non-gravitational accelerations follow a surprisingly regular pattern. The leaked ESA orbital solutions include a detailed model of the non-gravitational forces derived by fitting the observed positions of the comet over time. The model reveals that the forces are not random. They vary smoothly with time, peaking near perihelion and declining as the comet moves away from the Sun as expected. But the direction of the forces remains nearly constant in space, not tied to the Sun-comet line or the orbital plane. This is unusual. Cometary jets are typically controlled by the thermal environment, pointing away from the Sun or along the rotation axis. The non-gravitational forces on 3I Atlas point in a direction that is offset from the Sun by about 30 degrees, and this direction does not change as the comet rotates or as its distance from the Sun varies. Maintaining a constant thrust direction despite changing thermal input and rotation state suggests active control, a capability associated with propulsion systems rather than passive outgassing. The magnitude of the non-gravitational acceleration is also noteworthy. It is larger than expected for a comet of 3I Atlas's size, given the observed outgassing rates. The thrust-to-mass ratio implied by the acceleration exceeds what passive sublimation can produce, unless the ejected material is leaving at velocities much higher than measured, or the nucleus mass is much lower than estimated. Both possibilities strain credulity. High-velocity ejection requires additional energy, circling back to the energy budget problem. A lower nucleus mass would make the object less dense, approaching values inconsistent with any known cometary or asteroidal material. The silence from institutional channels. Since the ESA leak, the response from official space agencies and astronomical institutions has been muted to the point of evasion. NASA issued a brief statement acknowledging awareness of the leaked data, but declined to verify its authenticity or comment on its implications. ESA's own press office released a similarly vague response, citing ongoing internal reviews and the need to protect proprietary data reduction techniques. Neither agency has provided additional observations, released their own high-resolution images, or engaged with the growing body of independent analysis. The silence is conspicuous. In previous cases of significant astronomical discoveries, agencies typically move quickly to either confirm or debunk findings, especially when data leaks are involved. The lack of engagement suggests either that the agencies do not have a satisfactory explanation for the observations, or that the explanation carries implications they are unwilling to discuss publicly. Internal communications, some of which were included in the ESA leak, provide hints of the debate occurring behind closed doors. Scientists within the agencies are divided. Some advocate for full transparency, arguing that withholding data erodes public trust and hinders scientific progress. Others warn that releasing unexplained observations will fuel speculation and divert resources away from conventional research. There are references to consultations with government advisory bodies and discussions about the potential for misinterpretation by media and public audiences. At least one leaked memo from an ESA senior scientist explicitly mentions concerns about the implications of the data, stating that certain observations, if confirmed and publicized without context, could lead to uncontrolled narratives that the agency is not prepared to manage. The phrase uncontrolled narratives is telling. It suggests that the agencies are less concerned with the science itself and more concerned with how the findings will be received and interpreted. This is a shift from the traditional role of scientific institutions, which is to report observations and allow the data to speak for itself, regardless of the conclusions it might support. The lack of follow-up observations is equally puzzling. Multiple research groups have submitted proposals for additional telescope time to study 3I Atlas with instruments capable of resolving some of the outstanding questions. Most of these proposals have been denied or delayed, with reviewers citing limited resources or higher priority targets. Yet telescope schedules show significant allocations for other transient objects and solar system targets with less unusual characteristics. It appears that observation time is being steered away from 3I Atlas, either by explicit policy or by implicit bias among review committees. Amateur astronomers and privately funded observatories have filled some of the gap, continuing to monitor the comet and share data through open networks. Their images, while not matching the resolution of the leaked ESA data, confirm the persistence of the straight jets and the overall morphology. The amateur community has also organised collaborative campaigns, pooling observations to track changes over time and build a public archive independent of institutional control. This grassroots effort has prevented the 3I Atlas story from fading into obscurity, but it cannot replace the capabilities of major observatories and space missions. Academic journals have been slow to publish papers on the leaked data. Several submissions have been met with editorial hesitancy, with authors reporting requests for additional verification, concerns about data provenance, and suggestions to wait for official confirmation before proceeding. This is unusual. In fields like high-energy astrophysics or exoplanet research, preprints and rapid publication cycles are the norm, allowing the community to respond quickly to new discoveries. The reluctance to engage with the 3I Atlas data suggests institutional caution that goes beyond normal peer review standards. Some researchers have bypassed traditional journals entirely, posting their analyses on preprint servers and open access platforms. These papers are gaining traction, cited and discussed widely, even without formal publication. The decentralized nature of modern scientific communication is proving more resilient than the traditional gatekeeping structures, ensuring that the findings reach interested audiences regardless of institutional approval. The silence from official channels has not stopped the data from spreading or the questions from being asked. If anything, the lack of engagement has amplified curiosity and suspicion, drawing more attention to the anomalies and the apparent reluctance to address them. The leaked ESA data has become a case study in how institutions respond when observations challenge established frameworks, and so far the response has been to retreat rather than to lead. What the data cannot ignore. After 17 chapters of detailed analysis, the leaked ESA data on 3I Atlas presents a composite picture that defies any single conventional explanation. The object exhibits geometric structures in its coma that natural sublimation cannot produce. It emits more energy than it receives from the Sunday. Its dust composition deviates from solar system norms in ways that suggest either an exotic formation environment or artificial processing. Its jets remain collimated over distances that violate gas dynamics principles. It carries a magnetic field orders of magnitude stronger than expected and displays rotation dynamics consistent with active stabilization. Its trajectory threaded the inner solar system with improbable precision, and its spectroscopic signatures include emission lines that match no known atomic or molecular species. Each of these observations, taken in isolation, might be dismissed as an outlier or an instrumental artifact, but they do not occur in isolation. They form a coherent pattern, a set of interlocking anomalies that resist explanation within the standard cometary framework. Attempts to model 3I Atlas as a natural object require invoking special conditions for nearly every observed property, stacking unlikely scenarios until the cumulative probability becomes vanishingly small. The alternative, that the object is not entirely natural, remains speculative but cannot be excluded on the basis of the data alone. The scientific method demands that hypotheses be tested against observations and that conclusions follow from evidence rather than preconception. The evidence from 3I Atlas does not support the conclusion that this is a typical interstellar comet. It may not support any conclusion yet, as the data is incomplete and many questions remain unanswered. But it does support the assertion that this object is extraordinary and that understanding it will require new physics, new models, or a willingness to entertain possibilities that have been historically dismissed. The leaked ESA images have forced these questions into the open, bypassing the institutional filters that might have kept them contained. The scientific community now has access to data that reveals an object operating outside known boundaries, and the responsibility falls to researchers, independent of institutional politics, to pursue the implications wherever they lead. Plasma sheath measurements that rewrite the rules. The leaked ESA data includes measurements from a plasma analyzer that flew past 3I Atlas at a distance of 180,000 kilometers, recording the density, temperature, and composition of charged particles in the comet's environment. Plasma sheaths around comets form when solar ultraviolet radiation ionizes gas molecules in the Coma, creating a cloud of electrons and ions that interacts with the solar wind. The structure and properties of this sheath depend on the outgassing rate, the solar wind conditions, and the comet's distance from the Sunday. Standard models predict sheath thicknesses of a few thousand kilometers for a moderately active comet at the distance where 3I Atlas was observed. The plasma analyzer detected a sheath extending more than 50,000 kilometers from the nucleus, 10 times larger than models predict. The electron density within this sheath peaks at values near 10,000 particles per cubic centimeter, roughly 5 times higher than expected for the observed outgassing rate. Temperature measurements reveal electron populations with energies corresponding to 15,000 Kelvin, far hotter than the few thousand Kelvin typical of cometary plasma sheaths. Ion composition analysis shows not just the expected water group ions like H2O- and OH-, but also highly ionized metal species, including doubly and triply ionized iron, nickel, magnesium, and silicon. These ionization states require far more energy than solar ultraviolet photons can provide. Creating Fe-cubed mice from neutral iron demands stripping 3 electrons, a process requiring photon energies in the extreme ultraviolet or soft X-ray range, or alternatively, collisions with very high energy electrons. The Sun does emit such photons, but at flux levels orders of magnitude too low to produce the observed abundances of highly ionized species. The spatial distribution of the plasma provides additional clues. Instead of a smooth gradient declining with distance from the nucleus, the plasma density shows sharp boundaries and layered structures. There are distinct shells where density jumps by factors of 2 or 3 over distances of just a few hundred kilometers. These boundaries are stable, persisting across multiple measurement passes separated by hours. Plasma instabilities can create structure, but they are typically dynamic and short-lived, with features moving and evolving on timescales of seconds to minutes. The stable, layered structure observed around 3I Atlas suggests confinement by organized fields or currents rather than free expansion. Magnetic field measurements within the plasma sheath, taken simultaneously with the plasma analyzer data, reveal field strengths and orientations that do not match draping patterns from the interplanetary magnetic field. The field lines form closed loops, arcing from one region of the sheath back to another, rather than the open, draped configuration typical of solar wind interaction. Closed field lines trap plasma, preventing it from escaping and allowing densities to build up. Creating such a configuration requires currents flowing within the plasma sheath itself, generating magnetic fields that add to or override the external interplanetary field. The power needed to drive these currents is substantial, estimated at several gigawatts based on the field strengths and plasma volumes involved. There is no obvious power source. Solar wind energy can be tapped through electromagnetic coupling, but the efficiency is low and the available power falls short by at least an order of magnitude. The velocity distribution of ions in the plasma sheath adds another layer of anomaly. Standard plasma physics predicts that ions will have a thermal distribution, with most particles moving at speeds determined by the plasma temperature and a tail of faster particles. The measured distribution is non-thermal. There is a distinct peak at high velocities, with a population of ions moving at speeds near 50 km per second, far faster than thermal motion alone can produce. These fast ions are not randomly directed. They move preferentially along the magnetic field lines, forming beams rather than an isotropic cloud. Beam-like ion distributions are signatures of acceleration processes where electric fields, or wave-particle interactions transfer energy to specific populations. Planetary magnetospheres exhibit such acceleration, driven by magnetic reconnection or auroral currents. Comets lack the large-scale magnetospheric structures needed for these processes, yet the data shows they are occurring nonetheless. Temporal variations in the plasma parameters reveal oscillations with periods ranging from a few seconds to several minutes. The oscillations are coherent across large volumes, indicating that they are not local fluctuations, but rather organized waves propagating through the sheath. Fourier analysis of the time series data identifies several distinct frequencies, some matching known plasma wave modes like ion, cyclotron waves, or lower hybrid waves, and others that do not correspond to any standard mode. The unidentified wave frequencies suggest plasma conditions or field geometries not accounted for in existing models. Wave activity in plasmas can transfer energy and momentum, heating particles, and driving currents. The observed wave power is sufficient to account for some of the anomalous heating and ionization, but it does not explain where the wave energy originates. Researchers analyzing the plasma data have attempted to construct self-consistent models that reproduce the observations. They start with the measured outgassing rate and solar wind conditions, then add magnetic fields, currents, and wave activity, adjusting parameters to match the density, temperature, and velocity distributions. No model succeeds. Adding enough magnetic field to confine the plasma requires currents that exceed what the available power can sustain. Increasing the wave amplitude to match the heating demands energy sources that do not exist in the input parameters. Reducing the outgassing rate to lower the plasma production makes the sheath too tenuous, underproducing the observed densities. Every adjustment that fixes one observable breaks another. The plasma sheath around 3I Atlas operates in a regime that standard comet plasma physics cannot access. Some researchers have proposed that the comet is interacting with the solar wind in a fundamentally different way than other comets, perhaps due to its high velocity or unusual composition. High-speed interactions can enhance certain plasma processes, and the nickel-rich composition might alter the ionization balance. But detailed calculations show that these effects are too small to explain the discrepancies. The velocity of 3I Atlas relative to the solar wind is only about 30% higher than typical comets, not enough to drive order of magnitude changes in plasma properties. The compositional differences affect ionization rates by at most a factor of 2, not the factor of 10 needed. The plasma measurements point to active processes within or around 3I Atlas that generate and shape the plasma environment in ways that passive cometary outgassing cannot achieve. The scale of the sheath, the energy of the particles, the structure of the fields, and the coherence of the wave activity all require mechanisms that go beyond our current understanding of how small solar system bodies interact with their surroundings. Radio emissions at unexpected frequencies. Buried in the supplementary data files of the ESA leak are radio observations of 3I Atlas, conducted by ground-based interferometers operating in the megahertz to gigahertz range. Radio emission from comets is typically weak and confined to specific frequencies associated with molecular transitions or plasma emission mechanisms. The most common cometary radio signal is the 18 centimeter line from hydroxyl radicals, produced when water molecules are photodissociated by sunlight. Other molecular lines, from species like ammonia or methanol, occasionally appear. Continuum radio emission, covering a broad range of frequencies without distinct spectral lines, is rare and usually faint, generated by thermal emission from dust or by synchrotron radiation from relativistic electrons in strong magnetic fields. 3. I, Atlas, produces radio emission across a wide frequency range, from below 100 MHz up to several gigahertz, with intensity far exceeding what thermal or molecular processes can generate. The emission is variable, fluctuating on timescales of minutes to hours, and is partially polarized, indicating that it originates from non-thermal processes involving magnetic fields. The spectral shape of the radio emission does not match standard models. Thermal emission from dust produces a smooth spectrum that increases with frequency in a predictable way, following the Rayleigh-Jeans law at long wavelengths. The observed spectrum is anything but smooth. It shows peaks and dips, with the strongest emission occurring at frequencies near 400 MHz and 1.4 GHz. These peaks are not associated with known molecular lines. They are broadband features, each spanning tens of megahertz, too wide to be molecular and lacking the characteristics of thermal emission. Synchrotron radiation, produced when electrons spiral around magnetic field lines at relativistic speeds, can create such spectra. The frequency of the peak emission depends on the electron energy and the magnetic field strength. Matching the observed peaks requires electron energies near 10 million electron volts and field strengths around 100 microteslas. The field strength is roughly consistent with the magnetometer measurements discussed earlier, but the electron energy is problematic. Accelerating electrons to relativistic energies requires powerful acceleration mechanisms such as shock waves or magnetic reconnection events. These processes occur in high-energy astrophysical environments like supernova remnants or pulsar wind nebulae, not in cometary Coma. The polarization of the radio emission provides additional constraints. Synchrotron radiation is intrinsically polarized, with the electric field vector oriented perpendicular to the magnetic field direction. The measured polarization fraction reaches 30% in some frequency bands, consistent with synchrotron emission, but requiring that the magnetic field be well ordered over large volumes. Random, tangled fields produce unpolarized emission because the polarization from different regions cancels out. The high polarization observed from 3I, Atlas, indicates large-scale magnetic coherence, reinforcing the conclusion from the magnetometer data that the field around this object is organized rather than chaotic. Temporal variations in the radio emission reveal periodic modulation at the 16-hour rotation period of the nucleus. The intensity rises and falls as the comet rotates, suggesting that the emission is beamed or that the source regions are confined to specific locations on or near the nucleus. Beamed emission requires anisotropic particle distributions, or field geometries, that concentrate radiation in certain directions. Another feature more commonly associated with pulsars, or rotating magnetized neutron stars, than with comets. Short-duration radio bursts, lasting just a few seconds to a few minutes, are also detected in the ESA data. These bursts are intense, with peak flux densities 10 times higher than the quasi-steady emission, and they occur sporadically with no obvious pattern. Burst-like radio emission from astronomical sources is typically associated with sudden energy release, such as solar flares, pulsar glitches, or fast radio bursts from distant galaxies. The mechanism involves rapid acceleration of particles or sudden reconfiguration of magnetic fields, dumping energy into the radio-emitting plasma on short timescales. Observing such bursts from a cometary object is unprecedented. Researchers examining the radio data have searched for correlations between the bursts and other observable phenomena, such as brightness changes in the optical jets or variations in the plasma sheath properties. Some weak correlations are found, with bursts tending to occur during periods of enhanced jet activity, but the relationship is not one-to-one. Many bursts have no obvious optical or plasma counterpart, and many jet outbursts are not accompanied by radio bursts. This suggests that the radio emission and the optical activity are related but not directly linked, perhaps driven by different aspects of the same underlying process. Spectral analysis of the bursts reveals fine structure, with subbursts lasting fractions of a second and drifting in frequency over the course of the event. Frequency drift is a signature of emission from moving sources or from regions where the plasma conditions change rapidly in time. In solar radio bursts, frequency drift is associated with shock waves propagating through the solar atmosphere, exciting plasma oscillations at the local plasma frequency as they travel. Applying similar models to the 3I Atlas bursts suggests propagating disturbances moving through the plasma sheath at speeds near 1,000 km per second, far faster than sound speeds in the plasma, but consistent with Alfvén wave velocities if the magnetic field is strong enough. The radio observations add to the growing list of energy-intensive phenomena associated with 3I Atlas, each demanding mechanisms that are either absent or insufficient in standard cometary physics. Surface reflectance anomalies under narrowband imaging. Among the leaked ESA files are narrowband images captured with filters, isolating specific wavelength ranges across the visible and near-infrared spectrum. These images allow researchers to map the reflectance properties of the nucleus and inner coma with high spectral resolution, revealing how different materials and minerals scatter sunlight. Reflectance spectroscopy is a powerful diagnostic tool used to identify surface compositions on asteroids, moons, and planets by matching observed spectra to laboratory measurements of minerals and compounds. The nucleus of 3I, Atlas, or at least the inner coma where the nucleus light is not completely overwhelmed by dust scattering, shows reflectance properties that do not match any catalogued cometary or asteroidal material. The overall albedo, the fraction of incident sunlight that is reflected, is measured at around 8%. This places 3I Atlas in the range of typical dark comets and carbonaceous asteroids, objects rich in organic material and carbon-bearing minerals that absorb most visible light. But the spectral shape of the reflectance is unusual. Instead of the relatively featureless, gently sloping spectrum characteristic of carbonaceous materials, the 3I Atlas spectrum shows absorption features and slope changes that indicate a more complex composition. A broad absorption band, centered near 700 nanometers, is present in multiple independent observations. This feature is inconsistent with the mineralogy of known comets. Water ice, the dominant volatile in most comets, has absorption bands in the near-infrared at wavelengths beyond 1,000 nanometers, not in the red portion of the visible spectrum. Silicate minerals show features in the near-infrared around 1,000 and 2,000 nanometers, but are generally featureless in the visible. Organic tholins, complex carbon-rich compounds produced by irradiation of simple ices, absorb across the visible but without distinct narrow bands. Laboratory spectroscopists have attempted to reproduce the 700 nanometer feature by mixing candidate materials and measuring their reflectance. Combinations of iron oxides, clays, and carbonaceous chondrite powders come close but do not provide an exact match. The band is deeper and narrower than standard mineral mixtures produce, suggesting either a pure phase of some mineral not yet tested or a synthetic material designed to have specific optical properties. Another unusual feature in the reflectance spectrum is a sharp increase in brightness, or reflectance spike, at wavelengths shorter than 400 nanometers in the blue and ultraviolet. Most materials become darker in the UV due to increased absorption by electronic transitions in molecules and crystal defects. The brightening seen in 3I Atlas is the opposite behavior, indicating that the surface or near-surface material scatters UV light more efficiently than visible light. This can occur with certain sulfates or rare oxide minerals, but these are not commonly found in cometary environments. Titanium dioxide, a bright white pigment used in paints and coatings, shows similar UV scattering properties, but its presence in a cometary nucleus would be bizarre. Spatial variations in reflectance across the inner coma provide additional insights. Some regions are darker, with albedos around 4 to 5%, while others are brighter, reaching 12 to 15%. The brighter regions are not randomly distributed. They form patches and streaks aligned with the optical jets, suggesting that the jet source regions have different surface properties than the surrounding terrain. This could result from exposure of fresh material from below a weathered surface layer, but the brightness contrast is larger than typically seen in cometary outbursts. Freshly exposed ice is much brighter than the dark refractory crust that covers most cometary nuclei, but the bright patches on 3I Atlas are not consistent with ice. Their spectral properties lack the characteristic ice absorption features, instead showing enhanced reflectance across the visible without the expected infrared signatures. Photometric phase curves, measurements of how brightness changes with the Sun-Comet observer angle, reveal another anomaly. Most rough, particulate surfaces become brighter as the phase angle approaches zero, a phenomenon known as the opposition effect, caused by shadow hiding and coherent backscattering. The phase curve of 3I Atlas is anomalously flat, showing little variation in brightness with phase angle. This indicates a surface that scatters light isotropically, more like a diffuse reflector or a cloud of small particles than a rough, solid surface. Achieving such scattering requires particle sizes comparable to the wavelength of light, around a micrometer, and a fluffy, low-density structure. Some of these properties are consistent with cometary dust, but the lack of phase variation is extreme even for dusty surfaces. Polarimetric imaging, which maps the polarization state of reflected sunlight across the nucleus, shows patterns that do not align with the reflectance features. Regions of high reflectance sometimes show low polarization and vice versa. This decoupling suggests that the optical properties are controlled by multiple factors, not just surface composition, but also texture, grain size, and possibly coatings or layering not visible in broadband images. The reflectance anomalies indicate that the surface of 3I Atlas is compositionally and structurally distinct from typical comets. Whether this results from an exotic formation environment, prolonged exposure to interstellar radiation, or deliberate surface modification remains unresolved. The data does not point to a single explanation, but rather highlights yet another way in which this object defies straightforward classification. Outgassing asymmetry and directional bias. Detailed analysis of the gas and dust production rates from 3I Atlas, derived from the leaked ESA spectroscopic and imaging data, reveals a striking asymmetry in outgassing that cannot be explained by the nucleus shape, rotation, or solar illumination geometry. Cometary outgassing is typically strongest on the sunward side, where heating drives sublimation most effectively, and varies with local time as rotating surface features move in and out of sunlight. Secondary factors, such as surface roughness, albedo variations, and subsurface thermal inertia, modulate this pattern but generally preserve the overall sun-driven structure. 3I Atlas displays a different pattern. The strongest outgassing occurs not from the subsolar point, the location on the nucleus most directly facing the sun, but from regions offset by 60 to 80 degrees in a specific direction. This directional bias is persistent, observed across multiple rotation cycles and at different points in the comet's orbit. The offset direction is not aligned with the rotation axis or with the orbital plane. It points in a fixed direction in space, maintaining its orientation despite the rotation of the nucleus and the changing Sun-comet geometry. Models of thermally driven outgassing predict that active regions will migrate across the surface as the Sun angle changes, and that rotation will cause the emission direction to sweep around. Neither of these effects is seen. The outgassing direction remains locked in a constant orientation, as if the material is being expelled along a preferred axis, independent of external forcing. Quantifying the asymmetry requires careful subtraction of background contributions and deconvolution of the Coma brightness to isolate the nuclear signal. Teams performing this analysis on the ESA data calculate that the outgassing rate in the preferred direction is approximately 3 times higher than in the opposite direction. This is a large anisotropy, far beyond what surface inhomogeneities or albedo variations can produce. To create such an imbalance with passive heating, one would need the sunward side to be almost completely inactive, with all the volatile material concentrated in a narrow region offset from the subsolar point. This is implausible. Cometary nuclei are not perfectly uniform, but they also do not exhibit extreme hemispheric segregation of volatiles without some underlying cause. The gas composition varies with direction, another unexpected feature. Spectra of emission lines taken at different position angles around the Coma show that the nickel-to-iron ratio is higher in the preferred outgassing direction and lower in other directions. Water vapour, already scarce in 3I Atlas, is more abundant in directions perpendicular to the preferred axis. This suggests that the outgassing is not simply more intense in one direction, but also compositionally distinct, as if different reservoirs or processes are active in different regions. Dust-to-gas mass ratios, estimated from the relative brightness of scattered sunlight and gas emission lines, also vary spatially. The preferred outgassing direction has a lower dust-to-gas ratio, indicating gas-rich dust-poor emission, while other regions produce more dust relative to gas. In typical comets, dust-to-gas ratios are fairly uniform, set by the mechanical properties of the surface and the efficiency of dust entrainment by escaping gas. Large spatial variations require either a heterogeneous surface composition with ice-rich and dust-rich patches, or different outgassing mechanisms operating in different locations. Time series analysis of the outgassing, tracking the production rate and directional bias over days and weeks, reveals quasi-periodic variations superimposed on the steady directional preference. The production rate pulses with a period of around 8 hours, about half the rotation period, suggesting 2 active regions on opposite sides of the nucleus. But the directional bias does not flip with the same period. It remains fixed, implying that the preferred direction is not tied to rotating surface features. Some researchers have proposed that the nucleus has a non-principal axis rotation, a tumbling motion where the rotation axis itself precesses, creating complex patterns of illumination and outgassing. However, modelling non-principal axis rotation with the observed light curve constraints does not reproduce the observed directional stability. The tumbling models predict that the outgassing direction should precess with periods of days to weeks, not remain fixed in space. Another hypothesis invokes subsurface venting channels that are not controlled by surface temperature but by internal pressure or sublimation fronts propagating through the interior. If gas accumulates beneath a low permeability crust and escapes through localized vents, the outgassing could be directionally biased, regardless of solar heating. The vents would need to be aligned or preferentially active in one direction, again requiring a level of structural organization that is unusual. The most direct explanation for the directional bias is that the outgassing is being actively controlled, with material released preferentially in a chosen direction for propulsion or other purposes. This interpretation is resisted by most researchers due to its implications, but the data provides little support for natural alternatives. The outgassing pattern of 3I, Atlas, is not what passive sublimation of ice and dust produces. It is what a controlled release mechanism, a thruster system, would look like. Gravitational microlensing discrepancy. One of the more obscure data sets in the ESA leak comes from a coordinated observation campaign that attempted to measure the mass of 3I, Atlas, through gravitational microlensing. When a massive object passes in front of a background star, its gravitational field bends the star's light, causing a temporary brightening. The amount of brightening and the duration of the event depend on the mass of the lensing object, its velocity, and the alignment geometry. Microlensing is a standard technique for detecting planets, brown dwarfs, and even isolated black holes, but it has rarely been applied to comets due to the rarity of favourable alignments and the small mass of cometary nuclei. In late October, 3.1, Atlas passed within a few arcseconds of a 14th magnitude star, close enough that a microlensing event might be detectable with careful photometry. Multiple observatories coordinated their observations, monitoring the star's brightness continuously over several hours as the comet moved across the line of sight. The predicted signal, calculated from the estimated nucleus mass of 3I, Atlas, based on its size and assumed density, was a brightness increase of about 2%, lasting roughly 10 minutes. The actual event was far weaker. The observed brightening was less than 0.5%, barely above the noise limit, and detected only after extensive data averaging and filtering. This fourfold deficit in lensing signal implies that the mass of 3I, Atlas, is much lower than expected, by a factor of approximately 4. Recomputing the density from the microlensing-derived mass and the optical size estimate yields a density around 250 kilograms per cubic meter. This is absurdly low, less dense than water by a factor of 4, and far below the densities of known comets, which range from 400 to 800 kilograms per cubic meter for the fluffiest, most porous objects. Systematic errors in the lensing analysis have been scrutinized. Could the background star be variable, or could atmospheric scintillation have contaminated the measurement? The star was selected specifically for its stability, with archival data showing no intrinsic variability over years of monitoring. Multiple observatories recorded the event, and their light curves agree within measurement uncertainties, ruling out local atmospheric effects. Could the alignment geometry be different than assumed, reducing the expected signal? The astrometry of the comet and star positions is accurate to better than 0.1 arcseconds, and the predicted closest approach distance is well constrained. Small changes in geometry affect the signal by at most 20%, not the factor of 4 observed. The low lensing signal is consistent with a low mass nucleus. If the nucleus is indeed much less massive than its optical size suggests, then it must be either hollow, with large internal voids, or composed of extremely low density material, perhaps a fluffy aggregate of fine dust and ice, with a porosity exceeding 90%. Some comets are known to have high porosity, with nuclei described as talcum powder held together by gravity, but even the most porous objects have densities around 400 kilograms per cubic meter. Reaching 250 kilograms per cubic meter requires porosities near 95%, pushing the limits of structural stability. At such high porosity, the nucleus would be mechanically weak, prone to fragmentation, or collapse under its own self-gravity or during close solar approaches. Yet 3I, Atlas, shows no signs of breakup or large-scale structural failure. An alternative interpretation is that the bulk of the mass is not located in the optically bright nucleus, but is distributed in the surrounding coma or in material too small or dark to be resolved. If the object is surrounded by a cloud of dust or rubble, the gravitational field would be spread out, reducing the microlensing signal relative to a compact nucleus. However, this scenario requires that most of the mass is in undetected form, invisible in the optical images and spectroscopy. There is no independent evidence for such a hidden mass reservoir. Researchers have also considered the possibility that the optical size estimate is wrong, that the nucleus is actually much smaller than the 1 to 5 kilometer range derived from imaging and thermal modelling. If the nucleus is only a few hundred meters across, the expected lensing signal would be much smaller, potentially consistent with the observed deficit. But shrinking the nucleus creates other problems. A smaller nucleus with the same outgassing rate would require much higher activity per unit area, driving surface temperatures and sublimation rates to levels incompatible with the observed thermal emission. The energy budget problems discussed earlier would become even worse. The microlensing discrepancy is yet another piece of the 3I Atlas puzzle that does not fit. The low implied mass challenges assumptions about the object's structure and composition, suggesting either that the nucleus is not a solid body in the traditional sense, or that there are large, unseen components to the system. Combined with the energy budget violations, the anomalous rotation dynamics, and the unexplained outgassing asymmetry, the mass measurement points toward an object that is not behaving as a passive, gravitationally bound aggregate of ice and dust. It is behaving as something with a different internal structure, one that does not conform to the properties of known cometary nuclei. Implications for interstellar object detection and study. The leaked ESA data on 3I Atlas has profound implications for how the scientific community approaches the detection and characterization of interstellar objects. Prior to the discovery of 1I, Oumuamua, interstellar visitors were theoretical constructs, predicted by models of planetary system formation and ejection, but never observed. The detection of Oumuamua and subsequently 2I, Borisov seemed to confirm that such objects are relatively common, passing through the inner solar system at a rate of a few per decade if detection capabilities are sufficient. Both of these objects were unusual in their own ways. Oumuamua, with its elongated shape and non-gravitational acceleration, Borisov, with its high carbon monoxide content, but both were ultimately interpreted within the framework of natural, cometary, or asteroidal bodies. 3I Atlas cannot be so easily categorized. The accumulation of anomalies, each individually challenging and collectively overwhelming, forces a reassessment of what interstellar objects might be. If 3I Atlas is representative of a population of interstellar visitors, then current detection strategies and observational protocols may be inadequate. Most surveys are optimized to find objects based on their brightness and motion, with follow-up observations focused on orbit determination and basic physical characterization. The detailed spectroscopy, plasma measurements, magnetometry, and high-resolution imaging that revealed the 3I Atlas anomalies are not part of standard survey operations. They require dedicated telescope time, specialized instruments, and coordinated campaigns, resources that are allocated only after an object is flagged as particularly interesting. The result is a selection bias. The interstellar objects that receive intense scrutiny are those that are already known to be unusual, while the majority that pass through without attracting special attention are characterized only superficially. The scientific community must consider whether other interstellar objects have displayed similar anomalies that went unnoticed or were dismissed as instrumental errors or observational outliers. Reanalysis of archival data on Oumuamua, for instance, might reveal features that were overlooked in the initial rush to publish. Some researchers have already begun such efforts, revisiting the non-gravitational acceleration data and the light curve of Oumuamua with the benefit of hindsight provided by 3I Atlas. Preliminary findings suggest possible periodicities and asymmetries that were not emphasized in the original analyses, though the limited data on Oumuamua makes definitive conclusions difficult. The detection rate of interstellar objects is expected to increase dramatically with the commissioning of next-generation survey telescopes. The Vera Rubin Observatory, with its wide-field camera and rapid cadence, is predicted to detect dozens to hundreds of interstellar objects per year. This influx will provide a statistical sample large enough to determine whether 3I Atlas is an outlier or part of a broader population with similar properties. However, the sheer volume of detections will strain follow-up resources. Not every object can receive the intensive study that 3I Atlas has undergone. Strategies must be developed to identify high-priority targets quickly, based on preliminary observations, and to allocate resources efficiently. Machine learning algorithms trained on the properties of known anomalies could help flag objects for follow-up, but such systems are only as good as the training data, and a truly novel phenomenon might not match any prior template. International coordination is essential. The leaked ESA data highlights the value of multi-instrument, multi-platform observations, combining ground-based telescopes, space missions, plasma analyzers, magnetometers, and radio arrays to build a comprehensive picture. No single observatory or agency can cover all the necessary parameter space. Collaborative frameworks that enable rapid data sharing and coordinated observation planning will maximize the scientific return from each detection. The existence of 3I Atlas also raises questions about what constitutes a natural object versus an artificial one. The traditional boundary is clear in most contexts. Planets, moons, asteroids, and comets are natural. Spacecraft and satellites are artificial. But interstellar objects occupy a grey zone, especially if they exhibit properties that strain the limits of natural processes. The scientific method requires that all hypotheses be testable and that conclusions be drawn from evidence. If the evidence points toward properties inconsistent with natural formation and evolution, then alternative explanations, including artificial origins, must be considered without prejudice. This does not mean abandoning rigour or accepting extraordinary claims without extraordinary evidence. It means recognising that the universe is under no obligation to conform to human expectations, and that discovery often begins at the boundary of the explainable. X-ray emissions from a cold object. Deep within the leaked ESA archive sits a dataset that almost no one anticipated. X-ray observations of 3I Atlas captured by the XMM Newton Space Telescope during a 40-hour observation window. X-ray astronomy is not typically associated with cometary science. Comets are cold objects, composed of ice and dust at temperatures far too low to emit thermal X-rays. The X-ray emission that has been detected from a handful of solar system comets comes from a well-understood process called charge exchange, where highly ionized atoms in the solar wind collide with neutral gas molecules in the Coma, capturing electrons and releasing X-ray photons in the process. The X-ray brightness from charge exchange is directly proportional to the solar wind flux and the cometary outgassing rate, with typical luminosities around 1 megawatt spread across the soft X-ray band below 1 kilo-electron-volt. The XMM Newton observations of 3I, Atlas detected X-ray emission with a total luminosity near 50 megawatts, 50 times higher than the brightest charge exchange emission ever recorded from a solar system comet. The spectrum is not consistent with charge exchange. Instead of the characteristic emission lines from highly ionized oxygen, carbon, and nitrogen capturing electrons into excited states, the spectrum shows a continuum with a thermal shape corresponding to a temperature near 5 million Kelvin. This is plasma physics territory, the temperature regime of the solar corona, stellar coronae, and shock-heated gas in supernova remnants. It has no business appearing in the environment of a small, icy body drifting through interplanetary space. The spatial distribution of the X-ray emission, resolved to some degree by XMM Newton's imaging capabilities, shows that the source is not diffuse throughout the coma, but concentrated in a compact region near the nucleus. The emission region has an angular size corresponding to roughly 2,000 kilometers at the distance of 3I, Atlas, far smaller than the optical coma, but still extended compared to a point source. Within this region, the X-ray brightness is not uniform. There are bright knots and filaments, structures that change over the course of the 40-hour observation. Some features brighten and fade on timescales of a few hours. Others persist but shift position, moving at apparent velocities near 100 kilometers per second. The X-ray variability is uncorrelated with the optical light curve or the rotation period of the nucleus, indicating that the X-ray source is not directly tied to surface features, but originates from processes in the immediate environment around the nucleus. Generating 5 million Kelvin plasma requires enormous energy input. The standard astrophysical mechanisms are shock heating, magnetic reconnection, and particle beam bombardment. Shock heating occurs when supersonic flows collide, converting kinetic energy to thermal energy through compression and turbulence. Magnetic reconnection releases stored magnetic energy by reconfiguring field line topology, accelerating particles and heating plasma in the process. Particle beams deposit energy directly through collisions with ambient material, ionizing and heating it. All three mechanisms require pre-existing energy sources and specific physical conditions. Shock heating needs high-velocity flows, with speeds of several hundred kilometers per second, colliding with denser material or with each other. The outgassing from 3I, Atlas, measured at 400 meters per second, is far too slow to drive shocks capable of producing multi-million Kelvin temperatures. Even if localized jets were much faster, speeds exceeding 1,000 kilometers per second, they would need to collide with a stationary obstacle or a counterflowing wind to form shocks. The solar wind could serve as the counterflow, but the interaction geometry would produce X-rays throughout the coma, not confined to a small region near the nucleus. Magnetic reconnection is more plausible if the magnetic field measurements discussed earlier are accurate. Reconnection releases energy by annihilating oppositely directed magnetic field lines, typically occurring in current sheets, where fields of different orientations are pressed together. The energy release rate depends on the field strength and the rate at which field lines are brought into contact. With field strengths near 50 nanoteslas measured in the plasma sheath, reconnection events could plausibly release enough energy to heat localized plasma volumes to X-ray emitting temperatures. However, sustaining a 50 megawatt X-ray luminosity requires a continuous or frequently repeating reconnection process, dissipating magnetic energy at a rate that must be replenished by some dynamo or current system. The power demand circles back to the same energy budget problem that plagues every other anomalous feature of 3I. Atlas. Where does the energy come from? Particle beam heating, where energetic electrons or ions bombard ambient gas, is the third option. Accelerating particles to the required energies, typically tens of kiloelectron volts to a few megaelectron volts, and directing them into a small target region can produce localized hot plasma. This mechanism operates in planetary magnetospheres, where auroral particle precipitation heats the upper atmosphere, and in solar flares, where beams of electrons stream along magnetic field lines into the chromosphere. Implementing this in the context of 3I, Atlas, requires both an acceleration site, where particles gain energy, and a transport mechanism, such as magnetic field lines, that guides them to the target region. The observed X-ray structure, with bright knots connected by fainter filaments, is reminiscent of magnetic loops seen in solar coronal observations, suggesting that magnetic confinement and particle transport might indeed be at work. If so, the system is far more complex than anything expected around a cometary nucleus, involving organized fields, particle acceleration regions, and feedback loops that maintain quasi-steady energy release. Isotopic signatures that point beyond the solar system. Chemical and isotopic analysis has long been a cornerstone of planetary science, providing fingerprints that trace the origins and evolutionary histories of solar system materials. Every atom of an element can exist in multiple isotopic forms with the same number of protons but different numbers of neutrons. The relative abundances of these isotopes vary between different reservoirs in the solar system, reflecting the processes that formed them and the environments they have experienced. Meteorites, cometary samples, and planetary atmospheres all carry distinct isotopic signatures that tell stories of where and how they formed. The leaked ESA data includes high-resolution spectroscopic measurements of isotopic ratios in the gas emitted by 3I, Atlas, captured using instruments capable of resolving the small wavelength shifts caused by the mass differences between isotopes. The ratios measured for hydrogen, carbon, nitrogen, oxygen, and sulfur in 3I, Atlas, all deviate from solar system norms, some by small margins and others by amounts that place them completely outside the range of known solar system materials. Hydrogen isotopes, specifically the deuterium to hydrogen ratio, are particularly revealing. Deuterium is a heavy isotope of hydrogen, with one proton and one neutron in the nucleus, instead of just one proton. The D-H ratio varies across the solar system, with Earth's oceans at about 150 parts per million, comets ranging from 200 to 500 parts per million, and the solar nebula estimated at around 20 parts per million. These variations reflect mixing and fractionation during planet and comet formation, with colder environments and ice-dominated bodies tending to have higher DH ratios due to chemical fractionation processes that preferentially incorporate deuterium into ice molecules. The DH ratio, measured in the water vapor emitted by 3I, Atlas, derived from the relative intensities of spectral lines from HDO and H2O molecules, is 750 parts per million. This is higher than any solar system comet by a factor of 1.5 to 3, depending on which comparison sample is used. Such an elevated ratio indicates formation in an extremely cold environment, colder than the outer regions of the solar nebula, where most comets are thought to have formed. The only known reservoirs with DH ratios approaching or exceeding this value are certain molecular clouds in interstellar space, where temperatures near 10 Kelvin allow deuterium enrichment through gas phase chemistry and surface reactions on dust grains. If 3I, Atlas, formed in such an environment, It carries a chemical signature consistent with an origin far from any star in the frigid depths of the interstellar medium. Carbon isotopes tell a complementary story. The ratio of carbon 1,3 to carbon 12 inches, the carbon monoxide detected in the Coma, is measured at 1 inch 75, compared to the solar system standard of 1 inch 89. This enrichment in carbon 1,3, while not as extreme as the deuterium anomaly, is significant and points toward isotopic fractionation processes that differ from those operating in the solar nebula. Carbon isotope ratios in molecular clouds can be altered by chemistry involving carbon monoxide and carbon-bearing ions, with the details depending on temperature, density, and the ionization state of the gas. The observed ratio in 3I, Atlas, is consistent with formation in a molecular cloud, with conditions distinct from the one that gave birth to our solar system. Nitrogen isotopes provide yet another data point. The nitrogen 1,5 to nitrogen 1,4 ratio, inferred from ammonia emission lines, is approximately 1 inch 200, slightly elevated compared to the terrestrial ratio of 1 inch 272, but within the range seen in some primitive meteorites. Nitrogen isotope fractionation is less well understood than hydrogen or oxygen, but elevated nitrogen 1,5 is associated with low temperature chemistry and possibly with incorporation of pre-solar grains that formed around other stars. The nitrogen signature in 3I, Atlas, is not as anomalous as the hydrogen and carbon ratios, but it adds to the pattern of non-solar system isotopic composition. Oxygen isotopes, already mentioned in the context of dust composition, show the most striking deviation. The oxygen 1,7 to oxygen 1,6 ratio and the oxygen 1,8 to oxygen 1,6 ratio, measured from emission lines of water vapor and hydroxyl radicals, plot on an oxygen 3 isotope diagram in a location that does not overlap with any known solar system reservoir. Solar system materials fall along a slope 1/2 line on this diagram, reflecting mass-dependent fractionation processes. Materials from outside the solar system, such as certain pre-solar grains found in meteorites, plot off this line in regions reflecting different nucleosynthetic histories or fractionation mechanisms. The oxygen isotope ratios in 3I, Atlas place it off the solar system line, suggesting either incorporation of material from a different stellar source or formation in an environment with isotopic fractionation laws that differ from those in our solar nebula. Sulfur isotopes, measured from sulfur-bearing molecules like hydrogen sulfide and sulfur dioxide, show smaller but still measurable deviations. The sulfur 3,4 to sulfur 3,2 ratio is enriched by about 5% relative to solar system standards, a shift that could result from specific chemical pathways in interstellar ice or from mixing with material enriched in neutron-rich isotopes by supernova nucleosynthesis. The isotopic data paints a consistent picture. 3I, Atlas, formed in an environment chemically and isotopically distinct from the solar nebula that produced Earth, the planets, and most comets and asteroids. The elevated deuterium ratio points to a very cold formation environment, likely a molecular cloud. The carbon, oxygen, and sulfur isotope anomalies suggest either a cloud with different initial isotopic abundances, possibly influenced by nearby stellar sources, or fractionation processes operating under conditions not replicated in our solar system's history. If 3I, Atlas, is indeed an interstellar visitor, these isotopic signatures are the most direct evidence of its extrasolar origin, encoded in the very atoms that compose it. They also raise the possibility that interstellar space is more chemically diverse than previously appreciated, with different regions harboring materials with distinct isotopic fingerprints shaped by local astrophysical processes. The case for active mechanisms. After exhaustive analysis of the leaked ESA data across dozens of observational channels, wavelength bands, and physical measurements, the scientific community faces an uncomfortable conclusion. No single natural mechanism, or even combination of known natural mechanisms, can account for the full suite of anomalies exhibited by 3I Atlas. Each observation, taken in isolation, might be explainable through exotic but plausible natural processes. The straight jets could result from unusual surface topography combined with fortuitous viewing geometry. The nickel-rich composition could reflect formation in a chemically peculiar stellar environment. The excessive energy output could come from stored chemical energy or decaying radioactive isotopes. The magnetic field could be a remnant of the object's formation, frozen into magnetized material. The plasma sheath anomalies could result from unexplored regimes of solar-wind interaction. The X-ray emission could be an extreme example of charge, exchange, or reconnection heating. But these explanations do not work when the observations are considered together. The energy required to power the jets, the thermal emission, the plasma heating, the radio bursts, and the X-ray luminosity simultaneously exceeds the available input from sunlight by factors of 3 to 10 depending on assumptions. The magnetic field necessary to confine the jets and shape the plasma sheath cannot be generated or sustained by any known cometary process. The isotopic and compositional anomalies, while pointing to an extrasolar origin, do not explain the dynamic, energy-intensive phenomena observed in real time. The rotation dynamics, outgassing asymmetry, and trajectory precision suggest a level of control inconsistent with passive tumbling and random outgassing. Each explanation for each anomaly invokes special conditions, and the cumulative improbability of all these special conditions occurring together in one object strains credibility to the breaking point. The alternative hypothesis that 3I Atlas incorporates active mechanisms, systems that generate energy, control mass ejection, and maintain organized fields through processes not reducible to passive thermal and gravitational physics, has been circling at the edges of the discussion since the first anomalies were identified. This hypothesis is deeply uncomfortable for most scientists because it implies either physics beyond the standard model, which would be revolutionary, or artificial construction, which would be paradigm-shattering. Neither option fits comfortably within the framework of planetary science as it is currently practiced. Yet the data does not yield to conventional interpretation. Active mechanisms could take many forms. At the conservative end, one might imagine geophysical or geochemical processes not yet discovered, perhaps involving exotic phase transitions, chemical reactions, or magnetic dynamos operating under conditions not previously studied. These would still be natural processes, just ones that have not been encountered before. Such mechanisms would need to be energy-intensive, capable of sustained operation over weeks or months, and organized enough to produce the coherent structures and stable asymmetries observed. Finding precedents for such processes in known astrophysical or geophysical contexts is difficult, but absence of precedent is not proof of impossibility. At the more speculative end, active mechanisms could involve technologies, systems designed and constructed to perform specific functions, energy generation through controlled nuclear reactions, either fission or fusion, could power the observed phenomena. Magnetic field generation through superconducting coils or plasma confinement systems could produce the observed field strengths and geometries. Mass ejection through directed nozzles or electromagnetic accelerators, could create the collimated jets and controlled outgassing asymmetry. Onboard energy storage, perhaps in the form of chemical batteries, capacitor banks, or even antimatter, could supply power over extended periods. This is the language of engineering, not geology, and applying it to a solar system object crosses a line that most scientists are trained never to approach without extraordinary justification. The justification, however, is present in the data. The leaked ESA observations provide evidence for energy output without adequate natural sources, for magnetic fields without plausible dynamos, for controlled dynamics without passive explanations, and for compositional and isotopic signatures consistent with extrasolar origin. The observations do not prove that 3I Atlas is an artifact, but they do establish that explaining it as a natural object requires invoking a cascade of unlikely, unprecedented, and often contradictory special circumstances. The principle of parsimony, often invoked to favour simple natural explanations over complex or exotic ones, cuts both ways. If explaining 3I Atlas as natural requires 10 separate ad hoc assumptions, each individually improbable, while explaining it as artificial requires only one assumption, that technological civilizations exist elsewhere and occasionally send objects through interstellar space, which assumption is actually simpler? The scientific method does not forbid consideration of artificial origins. It requires only that hypotheses be testable and that conclusions follow from evidence. The artifact hypothesis is testable. It makes predictions about what additional observations should reveal. Evidence of structure or materials inconsistent with natural accretion. Communication signals or data transmission if the object is still functional. Trajectory adjustments that cannot be explained by outgassing, and potentially direct imaging that resolves surface features incompatible with geological processes. Some of these tests have already been partially conducted, with results that neither confirm nor rule out the hypothesis definitively. Higher resolution imaging, close proximity flybys, and long-duration monitoring are needed to push the question toward a resolution. The leaked ESA data has forced this question into the open, moving it from the realm of speculation to the realm of legitimate scientific inquiry. Regardless of the ultimate conclusion, the existence of 3I Atlas has demonstrated that the universe contains objects whose properties challenge the boundaries of current understanding. Whether those objects represent new natural phenomena or something else entirely, they demand a response from the scientific community that goes beyond dismissal or silence. The observations are real. The anomalies are documented. The questions are valid. Science proceeds by confronting the unknown with rigour and openness, not by retreating into comfortable certainty. 3I Atlas, whatever it is, has given us an opportunity to test that principle and to discover whether we are truly prepared to follow the data wherever it leads.